would be like a ridiculous amount of actual force in, if you had this, your fist being, 100 feet across or whatever it would be to scale.
Right.
But when you scale it down to an actual model that's just 12 feet high and you touch it, it's not going to have the same effect. It's like if you picture things like a toy boat bashing against the side of a bathtub or something like that, and then you compare that with a battleship moving very, very slowly and hitting a pier. Even though, it's the same type of thing to scale, it's very, very different because, the very, very large things have to be very, very heavy.
Yeah, true.
So there's all these problems, and, you really can't, unless you actually account for the problems and say what thing you are like, not modeling correctly, which thing you've had to change, then you can't really like say you've proved anything or demonstrated anything.
Okay, so in your view, what do you think is the best? Do you think a real physical model is the best, or do you think an actual digital version is the best, maybe?
I think physical models you can use to illustrate certain points, but if you want to illustrate what actually happened in total, I think you're going to have to do a digital model or a very large scale model, certainly not something that's only 1/100th the size. If you make your model 1/100th the size, then you need to have the density of that model be 10 times what the density of the World Trade Center itself would actually be. So if you did everything to scale, then you would have to add an extra 9 times the amount of weight to the building to make it work. And even then, you can't really do that everywhere.
Like every component would have to be...
Yeah, 10 times as dense. So and obviously you can't do something that's 10 times as dense as steel. So you're going to have to put the weight in somewhere else, which is why they're using these iron bricks in this Chinese example. So you can't really build an actual model, but you can illustrate certain points. Now, have you seen the model that I built where it's a bunch of wooden slabs held together with magnets?
Yeah, I think so. Yeah, that was the one I saw, I think. Right.
Yeah, and that's where I get up on a ladder and then I move the top of the building and I knock it down. Now, people say that's not a very good model because it doesn't. Obviously the floors weren't held together with magnets in the real building, and it seems like they would be a lot stronger because they had these metal connections. But when you look at the specifications of the building, they say that one floor slab was capable of supporting around 6 times its own weight as before it would collapse, basically. Now, the floor slabs don't support the weight of the building. The columns support the weight of the building.
Yeah,
and their columns are incredibly strong, and those aren't the things that fail. What fails are the floor slabs. So what I did was I built a model where the only criteria, other than it being able to stand up and not fall over when you hit the side of it, the only criteria was that the floors would support 6 times their own weight. And if you dropped something that weighed 6 times as much, I think I actually did up to 12 times as much, then a floor would fail.
Did you actually do that in your experiment?
Yeah.
Did you confirm that it could take up to 6 or 12 times?
Yes, I basically adjusted everything until it could support 6 times its own weight.
Wow.
And it actually you could do quite a lot more just by piling them on very, very carefully.
But that's very good. Okay, good.
Yeah, so I show that it can do this supporting 6 times its own weight, and then when you drop something on it, it progressively fails.
Right.
And it goes bam, down to the bottom, and then the columns fail because they're not supported from the side. But really, it was just showing that a collapse would progress all the way from the top to the bottom.
And I noticed also it was very, very fast also.
Yes, yeah, it's very, very fast, obviously because it's very, very small, and it's was it was kind of the same difference between free fall and well, the same difference from free fall as the actual collapses. You know, if you look at the actual collapses of the World Trade Center towers, then you see that there are parts of the building that fell off to the sides that go down faster than the collapse wave.
Yeah, for sure.
Because the collapse wave is being slowed by having to hitting the floors on the way down. So you get it's something like the bits that fell off the building right at the start, they reach the ground in about like 9 seconds or so, and the actual collapse wave is about 13 seconds, and then there's the columns in the middle that stay up for another like 5 or 10 seconds before they collapse as well. And right. I had the same kind of thing in my model as well. The first bits of wood that fell off to the side hit the ground in about, I don't know what it was, let's say it was like 1 second, and then the collapse wave of the final bits of the floor slabs, they hit the ground after about like 1.2 seconds, and then there was bits of the columns which stayed up for another half a second or so. So, kind of scale-wise, it was about the same type of thing as the real buildings. You've got the same events, but, really I was always trying to demonstrate was just this, that if the floors can only support 6 times their own weight, then a progressive collapse is inevitable.
So you actually got like something remaining standing in the middle, sort of? I don't remember if it was in the middle or where it was, but did you have something remaining standing after the collapse that happened?
It couldn't remain standing, but it's basically the floors got stripped away from the columns. So the columns kind of came down after the floors.
Okay.
Let me just have a look for it here.
It was some time since I saw it, so I more remember it was very, very fast, and that you did a very good illustration of the principle of it.
Yeah, it's very fast. And if you watch it in slow motion, though, you can you see what's going on a lot better. I'm just having a look at the actual thread that I have here.
Sure. I also have the one you showed earlier open.
Yeah.
No, I have talked to some people, and some people on the truther side, they are of course very much focused on what they consider free fall of the building, but the others, like Dave Thomas, thinks that it's very, very fast, but every floor makes a resistance, but it's very, very fast, almost like milliseconds or something. So that's why it is perceived as almost free fall, but each floor has a resistance, but it's very, very small, so you can't see everything.
Yeah,
you understand what I mean?
I do. There's a thing in 9/11 truth circles called the missing jolt, where they think that because the top is hitting the floors below it, there should be a jolt visible on the roof line.
Right.
But that's not what's going on. It's not like this big solid block is bashing through all the floors before. Once it starts to fall, it becomes essentially like a wave of debris, almost liquid-like. So it's more like dropping a whole bunch of rocks on top of the floors. Now, if you look at the image I just sent you, it's a frame from my video at like 1 minute 40 seconds, and you see you see kind of the collapse waves in there. There's the wave of the floors on the inside of the towers, and it's falling a different rate on each side, and the towers themselves it's the same on both sides. But you'll see there's also a piece of wood on the right hand side which has nearly reached the ground. So that's just falling a bit ahead. There's not that much difference here because it's a small model, but you see that the collapse wave is slower. And then you see the columns. There's the column in the middle, and then there's columns on either side, and those are they're falling down, but they are being left behind by the collapse wave, which is kind of
like the spindle in the middle, sort of. In the real towers.
Yeah, and I didn't do a very solid core column. So the core column, if I built it a bit more rigorously, it probably would have remained standing even more than that.
Right.
Yeah, and
but
you continue the video. It's the columns are still pretty much like 6 feet high when they were started at 8 when the wave has hit the ground, and then they fall. So it's actually quite similar to what happened in the World Trade Center in those two aspects. Obviously, it's very different in other aspects. And like you say,
of course, but it was very good.
You can't duplicate all aspects of the collapse in the scale model. It's simply impossible.
Okay. I was wondering also there about the modeling, or not about the modeling, about the actual collapse. Like for example, Richard Gage, he's sort of famous for doing his his thing that the bunkers love when he drops the cardboard boxes.
Yeah.
We love that meme, and when he did that on Hard Fire. But I was wondering, in real life, when the top part dropped, is it your understanding that it was like I think it was, that the top of the building sort of did not fall on it did not fall squarely on the columns below, but it fell sort of a bit to the side, so it fell actually on the floors, and that's why it fell so fast.
Yeah, well, definitely. Like if you look at World Trade Center 2 in particular,
right?
You can see that the top leaned over a very large amount, and even in World Trade Center 1, the columns are very big. They're several inches thick steel, and they're like that's not that much out of the total width of the building. The building was 200 feet wide, so it only needs to basically misalign the columns by about 2 or 3% of the building's position. So once the columns above are no longer aligned on the columns below, which they pretty much wouldn't be as soon as a column failed, because it would bend and it would shift to the side. It's not going to fail and then continue straight down. It has to have some sideways movement. So definitely what's happening is that the columns are not really an important factor anymore in terms of supporting the top of the building, because everything is falling past the columns. If you could somehow magically drop the top of the building exactly aligned on top of the columns and have the columns fail in such a way that it stayed aligned, then the collapse would be a bit slower and it might not even happen at all. But that's not what's happening. It's the floors that are failing, and the floors, as I described earlier, are very weak. They support 6 times their own weight, but the amount of building that's above them is hundreds of times the weight of an individual floor slab, because you've got all the columns and all the floors for the whatever it is, like 15 floors above the highest floor to fail. Right. So you're correct in what's going on is that it's falling past the columns and through the floors, and you see this in the collapse. You see column pieces poking out. You see it at the end of the collapses, but you also see it right at the start of the collapses. You see the core columns poking up above the collapse wave. So it's obviously not fallen through those columns. It's fallen past those columns. And which means it pretty much has to have fallen past all the other columns as well. If there's bits sticking out of the top, the only way they can get there is if the collapse wave has fallen past them. Yeah, true. And the core columns, were they the ones that supported the weight? Because sometimes I heard a bit conflicting theories, like some say that the core columns held up the most of the weight, and some others say that the perimeter columns held up most of the weight. Which is true? I think the core columns held up more of the weight. Okay. So I think I don't know the exact proportions, but I think there's more perimeter columns in terms of number, but the columns in the perimeter are a lot smaller than the core columns. If you look at the core columns, some of them are very substantial